Hi guys, welcome to our third video in chapter 25. This video is going to cover section 25.3, which is all about transmutation. And you can see again, objectives are pretty short. We want to talk about induced transmutation and how it's used to make larger elements. And we want to solve some problems using radioactive decay rates, okay? And a short list of vocab words for this video. So to jump into it, transmutation is the conversion of one atom, of an atom of one element into an atom of another element. So this is what ancient alchemists were always looking to do. They were trying to convert lead into gold. And so this is what was considered not possible for it was considered alchemy. People were trying to do it. And then in the 1700s, they realized it was impossible. But then in the 1900s, we actually saw Ernest Rutherford. Haha, Rutherford, our guy. He actually was able to get transmutation to happen. In lab, he bombarded a nitrogen 14 with a bunch of helium atoms, with a bunch of alpha particles, and he was able to get an alpha particle to stick into that nitrogen and create a very unstable fluorine atom, which had an atomic mass of 18 and an atomic number of 9, which then was able to break apart into our proton and our oxygen 17, another unstable oxygen atom. But indeed, he was able to get this transmutation to happen where he made an entirely new type of element. Okay. This is what's called induced transmutation. This is a nuclear reaction that's been artificially produced rather than happening spontaneously, such as in our radioactive decay of uranium into lead. That is spontaneous. This is an example of a induced transmutation. Okay. And just so you're aware, all transuranium elements, meaning elements with bigger, with an atomic number larger than 93, they have to be produced in lab through induced transmutation. And the most common way they're going to make those is actually through helium bombardment like this. They can also bombard it with neutrons as well. Um, but that brings me along to our next topic here, which is all about radioactive decay rates. And we want to be able to really understand what these are and start to look at how we solve these problems. And to start, I need to define a half-life, which is the time required for half of a radioisotope's nuclei to decay into its products. Okay, so we have really one formula that we need, but the basic formula is the amount remaining is equal to your initial amount times 1/2 to the power of n, where n is your number of half-lives that have passed. So this is the n that we are referring to here. Okay. So cool. So if I know I've gone 3 half-lives, well, I would take my initial amount, multiply it by 1/2 to the power of 3. And that's because after 3 half-lives, I've divided by half 3 times. So that's why we raise it to the exponent of 3. Now, often you will not know how many half-lives have passed. Instead, you'll just be given real time. Okay. So what we can do instead is use this potentially more useful formula here, which would be the amount remaining is equal to your initial amount times 1/2 of the elapsed time, lowercase t, divided by your length of your half-life, which would be capital T. Okay. And so that with this formula, you can actually solve for the amount remaining. You can solve for your initial amount. You can solve for time and figure out how much time has passed. You could even solve for the length of a half-life, depending on what information you're given. Okay. Now, each radioactive element will actually have its own specific half-life. And for example, for uranium, we saw in the previous video, uranium has a half-life of 4.5 billion years, very long time. Something like strontium has a more reasonable half-life of only 29 years. And you can see in our decay chart, what this is showing us is that if we start at 0 time with 10 grams, well, after 29 years, we should have half that much. So we should have 5 grams. So 10 times 1/2 is 5. Well, if we let that go another half-life after 58 years, we would expect that to be halved again, so down to 2.5 grams. Another half-life, we're up to 87 years, and we divide that by half again to 1.29 grams. Another half-life for a total of 116 years, and we divide it by half one more time, so we get to 0.625 grams. And what you can see is we're essentially multiplying it by 1/2 for every half-life, which hopefully makes sense because the half-life is how long it takes for half of it to decay. Okay, so that's how this works here. Now, if we're actually going to solve for things using this, it's actually going to involve using logarithms to solve for the exponent. Instead, you will most often be asked to solve for either the amount remaining or for the initial amount, which which reduces this to simple arithmetic, right? Here's a list of some half-lives for some radioisotopes. You can see uranium-238 has that 4.5 billion years, and then something like polonium 214 is only 163.7 microseconds. So it's very, very small, very, very small window of time. Radon 222 is only 3.8 days. And then tritium is 12.32 years. Tritium is a byproduct of nuclear explosion. So I also wanted to talk about radiochemical dating because there is a very important element called carbon-14. And carbon-14 actually has a half-life of about 5,730 years. And the cool thing about carbon-14 is that it's made by cosmic radiation in the atmosphere from nitrogen-14. Okay, so the nitrogen captures a neutron and forms and undergoes some radioactive decay to form a carbon-14, which is fairly rare in the atmosphere, but it can be absorbed by organisms, and it is decaying over time. Over 5,730 years is its half-life. So once it's in an organism, it's got a certain amount in that organism. And maybe we expect 1% of all of the carbon in a living organism to be carbon-14. Well, when that organism dies, it stops replenishing its carbon-14. And so the carbon-14 decays by beta decay. And the result is that we can actually look at how much carbon-14 is in a remaining sample, and we can use that to date how long it was since that thing was last alive and replenishing its carbon-14. So we can look at say a log underground, and we can measure like, hey, if only 12.5% of the carbon-14 we expect is remaining, we know that this must be 17,000 years old, roughly. So that's how carbon dating works. Again, something you may have talked about in your earth science class. All right, guys, thanks for listening. That's all I have for this video. I'll see you in the next one.